Welcome, chemists! This is the first of a two-part video series that will be discussing how changes in different factors can influence the kinetics of a reversible chemical reaction. My name is Kim, and our learning goals for this video are going to be to define concentration in terms of chemicals, to define pressure, right? What does it mean when we say pressure in terms of chemistry? And to explain how changes in chemical concentration and pressure affect the kinetics of a chemical reaction in terms of collision theory. We will be using some simulations to visualize our terms here. First, we'll talk about concentration. Concentration is describing the amount of a substance in a given unit of volume. It's often measured in molarity. You see that on the reference table as moles per liter, or parts per million, ppm, also found on your reference table. And you can think about concentration as a proxy for how many particles there are in a given amount of space of a particular substance. The higher the concentration of a substance, the more particles of a substance there are in a given amount of volume. The lower the concentration, the fewer particles there are in a given amount of volume. It's analogous to density in a solid, but concentration is often used as a measurement for describing solutions, so substances that are dissolved into water. Oftentimes, we are talking about a solute when we talk about concentration. The solute is the substance that was placed into the water to dissolve. So a higher amount of solute in a given amount of water means a higher concentration and a higher number of solute particles compared to a lower concentration. Let's think about concentration using a PhET simulation. Concentration is often measured by conductivity meters, and those meters will give you often a reading either in parts per million, in grams per milliliter, or in this case in moles per liter. So it's telling me how many moles of a substance, in this case copper sulfate, CuSO4, would be found in 1 liter of this whole solution of water. Right now, because I have not added any copper sulfate to the solution, the concentration is 0.00 moles per liter of copper sulfate in this water solution. I am going to add copper sulfate to the solution. So I'll add 2 shakes there. Notice I have increased the concentration to 0.309 moles per liter, and the color of the solution has gotten darker blue. You might be familiar with this idea if you've ever mixed lemonade for yourself or any other drink for yourself that involved mixing a powder with water, and you notice that the color gets more and more dramatic the more of that powder you add. Kool-Aid powder does the same thing. And so as I add more copper sulfate solution, you can see the concentration will increase even more. There's even more particles, more moles of CuSO4 per liter of CuSO4. So the higher the concentration of a solution, the more particles of CuSO4, in this case, there are in a given amount of space. The lower the concentration, so if I add some more water back to this, the lower the concentration, the fewer CuSO4 particles there are in a given amount of space. You can think about it as measuring how far apart the CuSO4 particles are from each other. Now let's think about pressure. If concentration is often a way to describe how many particles there are in a given amount of volume and are often describing solutions, which we think of as liquids, pressure is a different sort of physical term. Pressure is referring to gases most often, though not always, and pressure is really measuring the amount of force that is exerted on a given area. So instead of measuring the amount of a substance in a given volume, it's measuring how much force is being exerted on a given area. Common units include pascals or kilopascals, kPa, and atmospheres, atm. And when you think about pressure, what we're really saying when there is a higher pressure is that there is a stronger force being exerted on a given amount of space. When there is a lower pressure, there is a weaker force being exerted on a given amount of space. And so this is usually a measurement for gases. We can't see gases. Since gases are not visible, when gases are involved in chemical reactions and we're trying to think about gases in terms of collisions, it's really useful to think about this idea of pressure and to visualize what pressure is telling us. In this PhET simulation, the pressure needle here is telling us that there are 592 kilopascals of pressure when there are this number of gas particles, these purple particles here, at 27 degrees Celsius. If we count how many collisions are happening with the walls of the container, we can see that in 10 seconds, there were 36 collisions of different particles with the walls of the container. That's how pressure is being measured here. That's kind of why that gauge is connected there. So let's see what happens if we add more particles. So if we add more particles to the simulation, notice the pressure has increased here to 1,077 kilopascals. Let's see what happened to the number of collisions being measured in 10 seconds as well. Notice how that number of collisions has also increased to 63 wall collisions of the gas particles with the container in 10 seconds. So really, when we're talking about a gas, when we are thinking about the force that's being exerted on a given area, so like in this case, the force that's being exerted on this pressure gauge right here, that force comes from the particles actually hitting the walls of the container. So you can see how with a gas, the higher the pressure, the more particles of gas there must be. The lower the pressure, the fewer particles of gas there must be. As we decrease the number of particles, we see the pressure goes back down. The number of collisions in a given amount of time, or the amount of force being exerted on the walls of the container, also decreases. This first question asks you, what unit can be used to express the concentration of a solution? I will tell you, if you cannot remember from this video, it is always a good idea to check your reference table. There may be something there to help you. Hopefully, after checking your reference table, and please pause the video if you haven't come up with your answer yet, you notice that table D has the list of selected units, and I actually do see some of the units on here on the reference table. I don't see liters per second, but that looks like it's probably a rate because it's something per second. I don't see joules per gram, but that's going to have something to do with energy because of the unit joules, so that's probably not it. kPa I see here. I see PA, and kPa would mean kilopascals, but that says that it has to do with pressure. So ppm, parts per million, that is the unit that has to do with concentration according to the reference table. So I'm going to select option number 3. This next question says each of 4 test tubes contains a different concentration of HCl-AQ at 25 degrees Celsius. A 1 gram cube of zinc is added to each test tube. In which test tube is the reaction occurring at the fastest rate? I'm going to let you pause this video, take a moment to look at each of the 4 options and read the descriptions above and to the side of each one before selecting which tube you think the reaction will occur at the fastest rate in. Make sure to pause the video if you haven't come up with your answer yet. So I'm going to annotate the problem a little bit to show you what jumped out at me. I noticed that it said at 25 degrees Celsius and that it was talking about all 4 of those test tubes at 25 degrees Celsius. I also noticed that it said a 1 gram cube of zinc is added to each test tube, and I noticed that next to each test tube it says 10 milliliters. So I can make a list of things that are the same about all of the test tubes, my constants, and that would be that the temperature is 25 degrees Celsius, that each of the test tubes is getting 1 gram, equal amounts of zinc added to it in the shape of a cube, and that each test tube contains 10 milliliters of HCl. So how are the test tubes different? How can I choose my answer? Well, I noticed that there's this annotation that says 1m, 0.1m, 0.01m, and 0.001m, and it's a capital M. So again, looking back at table D on the reference table, that capital M there means molarity, and it is a unit of solution concentration. So I want to think which concentration will lead to the fastest reaction rate, because that is the only thing different about these 4 options. And so I will pick the highest concentration, because remember, the higher the concentration, if everything else is the same, the more solute particles, or in this case, the more HCl particles will be in that test tube. So the 1M test tube has more HCl particles in it than the 0.1M test tube, or the 0.01M test tube, or the 0.001M test tube. The 1 molar test tube has the most HCl particles, and since all of the test tubes are getting the same number of zinc particles added to them, test tube number 1 will allow for the fastest reaction rate, as it has the most HCl of all the possible setups. Finally, nitrogen, hydrogen gas, and ammonia gas are in equilibrium in a closed container at constant temperature and pressure. The equation below represents this equilibrium. We haven't talked yet about equilibrium, but equilibrium just means that there is both a forward and a reverse reaction happening. You can see this double arrow here, and it means that the forward and the reverse reactions are happening at the same rate. You'll hear more about that later, but for now, that's all you need to know. The graph below shows the initial concentration of each gas, the changes that occur as a result of adding H2 gas to the system, and the final concentrations when equilibrium is reestablished. All right, so a lot of words in there. We don't totally know what equilibrium means, but let's just read what the question is going to ask us and see if we can come up with an answer based on what we know. Explain, in terms of collision theory, why the concentration of H2 gas begins to decrease immediately after more H2 gas is added to the system. So I can see there's a spot on the time graph where H2 is being added. I see this sharp increase where H2 has been added to the system, and that right after that happens, the amount of H2 decreases. Now this might seem strange to you. You added more H2, the amount of H2 increased, and then it decreased. But let's think about collision theory. So H2 and N2 are the reactants in this reaction. They are reacting to form NH3. Adding more H2 particles to the system will cause there to be more H2 collisions with N2. So once I've added more H2 particles, there will be more H2 particles to collide with the N2. More collisions between N2 and H2 will increase the probability that those two particles will have an effective collision and actually be able to react to form NH3. This will increase the reaction rate of N2 and H2, which in turn will decrease the amount of H2 as it gets its bonds broken and reformed to form NH3. So in terms of collision theory, adding more H2 to the system will increase the number of collisions between H2 and N2, increasing the rate of reaction. In other words, increasing the rate that the H2 gets used up. We'll continue to think about these questions that involve changing the system and then thinking about what will happen in response. But remember, all we're thinking about with collisions is just what's causing the particles to hit each other and how will that impact the rate of our reaction. Let's check back in on our learning goals. Hopefully you feel more comfortable defining concentration, pressure, and explaining how changes in concentration and pressure can impact the kinetics of a chemical reaction, thinking about particle collision theory. The next video is going to discuss the impact of temperature and surface area on rates of reaction. Way to go.